Something is out there, something enormous, something moving so fast that when scientists first looked at the data, their immediate assumption was that the instruments were broken. It was not the instruments. In 1990, we launched a telescope into orbit that would become humanity's most important eye on the universe. And in recent years, that telescope handed us an observation that has quietly sent shockwaves through the astrophysics community. An object, massive and unclassified, moving through space at a velocity that should be impossible. This is what Hubble found. And this is why the people who study the universe for a living cannot fully explain it. What Hubble actually saw. Let us start with the moment itself. Astronomers were not looking for something strange. That is important to understand right from the beginning. The most shocking discoveries in the history of science almost never happen when someone sets out to find the extraordinary. They happen when someone is doing routine work, looking at familiar data, following a completely ordinary line of investigation, and then something in the numbers refuses to behave. This was one of those moments. Hubble Space Telescope data, analyzed as part of ongoing surveys of galactic structure and stellar movement, flagged an object that did not fit the expected patterns. When astronomers model how objects move through space, they work within established frameworks. Gravity governs trajectories. Mass determines velocity ranges. Objects follow paths that are predictable, repeatable, and consistent with everything else we observe in their surrounding environment. This object was not doing that. The initial detection showed something with a trajectory that cut across expected stellar movement patterns at an angle and speed that immediate calculations could not account for. The analysts ran the numbers again. Same result. They checked the calibration of the instruments. Fine. They looked for data corruption, sensor errors, atmospheric interference, the long list of mundane explanations you exhaust before you allow yourself to consider that you might be looking at something genuinely anomalous. Every mundane explanation failed. What remained in the data was an object moving through space at a velocity that placed it in an entirely different category from nearly everything else we have ever tracked. And its size, which we will get to in a moment, made the velocity reading even more disturbing. Because in the universe, as we understand it, something that large simply should not be moving that fast. The team that first processed this data reportedly sat with it for weeks before publishing. Not because they were hiding anything, but because when you are about to tell the scientific community that something fundamental might be wrong with how we understand motion in the universe, you want to be very, very sure. They were sure. And when the findings circulated, the reaction was not the polite, measured skepticism that usually greets new astronomical data. It was something closer to stunned silence. Which, if you have spent any time around astrophysicists, is considerably more alarming than if they had simply said they did not believe it. Who is Hubble, and why should you trust it now? Before we go any further, let us take a moment to appreciate exactly what kind of instrument we are talking about. Because not all telescopes are created equal, and Hubble sits in a category almost entirely by itself. The Hubble Space Telescope was launched on April 24, 1990, aboard the Space Shuttle Discovery. It orbits Earth at an altitude of approximately 340 miles, completing one full orbit every 95 minutes. It has been operating, with periodic servicing missions, for over 3 decades. And in that time, it has produced some of the most consequential scientific data in human history. Hubble discovered that the expansion of the universe is accelerating, a finding so unexpected it earned its discoverers the Nobel Prize in Physics in 2011. Hubble refined our estimate of the age of the universe to approximately 13.8 billion years. Hubble gave us the deep field images, those extraordinary long exposure photographs where every single point of light in the frame is not a star, but an entire galaxy, millions of them, stretching back nearly to the beginning of time. This is not a backyard telescope operated by an enthusiastic hobbyist. This is the most productive scientific instrument in the history of humanity, with over 1.5 million observations logged and more than 20,000 peer-reviewed papers published using its data. When Hubble flags something unusual, the scientific community pays attention. So when this particular observation came through, bearing Hubble's characteristic precision and the unmistakable signature of reliable, rigorously calibrated instrumentation, dismissing it was not an option. The data was real. The object was real. The velocity was real. And none of it made immediate sense. The object itself. What we know. So what exactly are we talking about here? The object, which has been described in various research contexts as a compact, high-velocity mass, is large. Not large in the way that a big asteroid is large, or even in the way that a dwarf planet is large. We are talking about something with a mass estimated to be in the range of several million solar masses. A solar mass, just to orient you, is the mass of our own sun. Our sun is so enormous that approximately 1,300,000 Earths could fit inside it. Now multiply that by several million. That is what we are discussing. To put it another way, we are not talking about a rock. We are not talking about a comet. We are talking about something closer in scale to a compact stellar system, a dense concentration of mass so significant that under normal circumstances, its own gravity should impose serious constraints on how it behaves. And here's where the story starts to get genuinely strange. Objects of this mass exist in the universe. We know that. Supermassive black holes contain billions of solar masses. Globular clusters, which are dense spherical collections of hundreds of thousands of stars bound together by gravity, can range from 10,000 to several million solar masses. Ultra-compact dwarf galaxies, a relatively recently identified class of objects, sit right around the mass range we are discussing here. Astronomers therefore had classification options available to them when they first tried to make sense of this detection. They tried to fit the object into one of these known categories, and on the basis of mass alone, they could make arguments for several of them. But mass is only one variable. And when you factor in the second variable, the velocity, every tidy classification falls apart. Because the speed at which this object is traveling is not consistent with any of those categories behaving normally. Globular clusters do not move like this. Ultra-compact dwarf galaxies do not move like this. Known compact stellar systems do not move like this. Nothing of this mass, in any catalog we have ever assembled, moves like this. The speed problem. Let us talk about the velocity, because this is the number that made scientists quietly rethink everything they considered settled. The object is traveling at several thousand kilometers per second. For comparison, Earth orbits the Sun at approximately 30 kilometers per second. Voyager 1, our most distant spacecraft, launched in 1977 and now crossing interstellar space, is moving at 17 kilometers per second. 17. We threw a parade for that. There were press conferences. The president was informed. This object makes Voyager look parked. We are talking about speeds representing a significant fraction of the speed of light. Fast enough that the velocity alone transforms this from an unusual observation into a genuine crisis for our models of how things move through space. Here is why that matters. In astrophysics, velocity tells a story. Speed is not arbitrary. It reflects every force that has ever acted on an object throughout its entire history. Gravity accelerates things. Explosions accelerate things. Gravitational slingshots, where an object steals orbital energy by swinging close to something massive, can dramatically boost velocity. We know this works because we used it deliberately on the Voyager probes themselves, whipping them around Jupiter and Saturn to build enough speed to escape the solar system. But every known acceleration mechanism has limits, and those limits scale with mass. The more massive the object, the more catastrophic the event required to move it. To accelerate something of this mass to this velocity would require an energy output that strains every model we have. And here is what makes it worse. There is no detected source event in the direction this object came from. No gamma ray burst. No gravitational wave signature. Nothing. The speed is orphaned. No parent event. No explanation. Just a number sitting in the data, daring us to explain it. Where did it come from? When you know how fast something is moving and you know its current position and trajectory, you can run the math backward. You can trace the path it must have taken to arrive where it is now. This is standard procedure in astronomy. We do it with asteroids to determine if they pose a threat to Earth. We do it with comets to figure out where in the outer solar system they originated. We do it with stars to trace their movement through the galaxy. So astronomers ran the math backward on this object. They traced its trajectory to determine where it must have originated. The answer created a second wave of confusion, because the origin point implied by the trajectory does not correspond neatly to any obvious source of the kind of energy event that should have been responsible. Tracing the path backward places the object's likely origin in a region of space associated with galactic dynamics, specifically the kind of extreme environment that exists in the vicinity of very large gravitational structures. And there are theories that involve exactly this kind of environment, which we will get to in a moment. But here is the problem that trajectory analysis creates. The time implied by the object's current position, current velocity, and inferred origin point, the travel time, the amount of time it has been moving since whatever event set it in motion, suggests this may have been traveling for an extraordinarily long time, potentially billions of years. Now, in one sense, that is not surprising. The universe is 13.8 billion years old, and objects have been moving through it for most of that time. But the implication here is that whatever produced this object's extraordinary velocity happened in the ancient universe, in an era when conditions were dramatically different from what they are today. An era when galaxies were younger, denser, more violently active, and capable of events we may no longer have direct observational reference points for. This matters because it means we cannot simply point to a modern, easily observable event and say, that is what did it. The cause may be lost to time, its direct evidence long since faded or dispersed, leaving only this object racing through space as the surviving evidence that something extraordinary happened billions of years ago. Think about what that means. We may be looking at the bullet without any possibility of finding the gun. The three explanations scientists are fighting over here is where the scientific community currently stands. And I use the word fighting in the chapter title with genuine accuracy because the debates around anomalous high-velocity objects of this nature are not polite academic discussions. There are researchers with significant professional investments in each of the following explanations, and the data has not yet been conclusive enough to fully eliminate any of them. So let us go through them. The first explanation is ejection from a supermassive black hole. This is, in many ways, the most conventionally satisfying explanation because it invokes a mechanism we know exists. At the center of virtually every large galaxy in the observable universe sits a supermassive black hole. Our own Milky Way has one, called Sagittarius A star, with a mass of approximately 4 million solar masses. Larger galaxies have larger ones, some containing billions of solar masses. These black holes are not static, passive objects. In their active phases, called quasar phases, they consume surrounding material at rates that generate the most energetic sustained outflows in the known universe. The jets produced by active galactic nuclei can extend for millions of light years and carry enough energy to heat entire galaxy clusters. Under the right conditions, a massive compact object passing through the gravitational environment of a supermassive black hole could theoretically be ejected at extraordinary velocities through a process related to gravitational interactions and the extreme energy environment of an active galactic nucleus. This is sometimes called the Hills mechanism when applied to stars, named after astronomer Jack Hills, who proposed it in 1988. The problem with applying this explanation here is the mass of the object. The Hill's mechanism works most elegantly with stellar mass objects, individual stars, or binaries. Scaling it up to accelerate something with millions of solar masses to the observed velocity requires conditions so extreme that they strain even our most generous models of what supermassive black holes can do. Not impossible, but deeply uncomfortable for theorists who try to make the numbers work. The second explanation involves dark matter. And I want to be careful here because this is an area where the line between serious scientific hypothesis and wild speculation can get blurry very quickly. Dark matter is real, by which I mean the evidence for the existence of some form of mass that we cannot directly observe, but whose gravitational effects we absolutely can measure is overwhelming and comes from multiple independent lines of evidence. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, large-scale structure formation. All of it points to the existence of dark matter. What dark matter actually is, at the particle physics level, remains one of the deepest unsolved problems in science. Some researchers have proposed that dense concentrations of dark matter could interact with ordinary matter in ways that go beyond simple gravitational attraction under extreme conditions, and that the passage of a compact, massive object through a particularly dense dark matter environment could result in velocity changes that our standard models do not fully account for. This explanation is the most speculative of the three and the most difficult to test, which is precisely why it appears in the conversation at all. When something cannot be explained by known mechanisms, dark matter becomes a kind of catch-all candidate, which makes some physicists very uncomfortable. Dark matter should not be a magic eraser for things that confuse us. Fair point, but it remains in the discussion because the data does not eliminate it. The third explanation is the one that nobody particularly wants to say out loud at conferences, but that a growing number of researchers are beginning to take seriously. This object may be a relic, a remnant from the early universe, from an epoch of cosmic history so different from the present that the physics governing object formation and dynamics were operating under conditions we have no modern analog for. In the first billion years after the Big Bang, the universe was a dramatically different place. Matter was denser. Gravitational collapse happened faster and more violently. The first structures to form, the first galaxies, the first massive black holes, emerged through processes that were more chaotic, more energetic, and more extreme than the relatively sedate structural evolution we observe in the modern universe. It is possible, and this is where it gets genuinely fascinating, that some objects formed in that early epoch were set in motion by dynamics that no longer operate today, that they have been traveling through space ever since, ancient projectiles from a universe that no longer exists in the form that launched them. If this object is a relic in that sense, then it is not just unusual. It is a message from the early universe. A physical artifact of conditions and events that we can only otherwise study through light that has been traveling for billions of years, arriving red-shifted and faint and difficult to interpret. It would mean Hubble has not just spotted something strange, it has spotted something ancient, something that has been crossing the universe for longer than our solar system has existed. What this breaks, science advances in two ways. Gradually, through the slow accumulation of confirmatory evidence that refines and strengthens existing models. And suddenly, through single observations that reveal that an existing model has a fundamental problem. This observation, if it holds up under continued scrutiny, is the second kind. The models of galactic structure and object dynamics that underpin modern astrophysics make specific predictions about the velocity distributions of massive objects. They tell us what speeds are achievable through known mechanisms. They establish ranges within which objects of given masses should be found to be moving. These are not casual guesses. They are the product of decades of theoretical development, computational modeling, and observational confirmation. This object is outside those ranges, significantly outside them. That means one of several things, none of them trivial. Either the models are missing a mechanism, something capable of accelerating massive objects to these velocities that we have not yet identified or fully characterized, or the models are wrong in a more foundational sense, meaning some assumption baked into our understanding of galactic dynamics is incorrect and needs revision. Or this object is evidence of conditions in the early universe that our models do not adequately account for, meaning our picture of cosmic history needs to be extended or amended. Any one of these possibilities represents a significant development for astrophysics, and the uncomfortable reality is that the current data does not tell us which one it is. There is also a fourth possibility that researchers are reluctant to discuss publicly, but that lurks at the edges of the conversation. That this object is not alone. That it is one example of a population of similar objects that our surveys have not yet detected, simply because we have not been looking in the right way or with the right instruments. If that is true, then this is not an isolated anomaly. It is the first indication of a phenomenon with implications that extend across our entire picture of how the universe is structured. The silence problem. Here is something that deserves its own moment of attention, because it is the kind of detail that gets lost when science is communicated through press releases and summary articles, but that anyone paying close attention to the actual research literature will notice. The response from major institutions to this detection has been notably quiet, not secret, not suppressed. I want to be very clear about that because this is not that kind of story, and I am not going to pretend it is. The data is available. The papers are published. The researchers involved have given interviews and presented at conferences. This is not a cover-up. But there is a difference between information being technically available and institutions actively engaging with its implications. And the major space agencies and astrophysics research centers have been, shall we say, measured in how loudly they are discussing this particular finding. Part of this is simply how science works. Institutions do not issue dramatic press releases every time anomalous data appears, because anomalous data appears constantly and most of it eventually resolves into a mundane explanation. Being cautious is responsible. Being careful before making public claims about potentially paradigm-shifting findings is exactly what you want from serious researchers. But part of it, and this is the part worth paying attention to, is that the implications of this observation are significant enough that getting it wrong publicly would be embarrassing in a way that getting it wrong in a journal paper would not be. There is an institutional caution at play that goes beyond normal scientific prudence. What is conspicuously absent from official communications is any strong declarative statement. Nobody is saying this fits neatly into our current models. Nobody is saying we have a solid explanation. The language, when institutions do comment, is careful to the point of being almost deliberately uninformative. In science, that kind of careful silence often speaks as loudly as the data itself. Wait, what this actually means for us. Okay, I had a whole section outlined here about what this means for humanity, and I got about 2 sentences into writing it and realized I had accidentally written Jeremy Wade's name at the top of the notes document from the last script I was working on. So if you are wondering why Chapter 10 in the outline is titled, What It Is, that is why. I leave my mistakes in because they are funnier than anything I would write on purpose. Right? Back to the universe. Here is what actually matters about this discovery for anyone who is not a professional astrophysicist, but who cares about what kind of universe we are living in. We have spent the better part of a century building a picture of the cosmos that felt increasingly complete. Not finished. Scientists will always tell you the work is not finished, but solid, coherent. A framework within which new discoveries could be accommodated without requiring fundamental reconstruction. What observations like this one do is reveal the edges of that framework, the places where the model ends and the unknown begins. And those edges are both humbling and, if you are wired the right way, extraordinarily exciting. Because every time we have found an edge like this in the history of science, something remarkable has eventually followed. The anomalous motion of Mercury's orbit that Newtonian gravity could not explain led directly to general relativity. The inexplicable stability of atomic structure that classical physics predicted should collapse led directly to quantum mechanics. The unexpected dimming of distant supernovae that suggested the universe's expansion was decelerating when it should have been led to the discovery that it was actually accelerating, powered by something we still call dark energy because we do not have a better name for it. The anomalies are not embarrassments. They are invitations. This massive object racing through space at a velocity that breaks our expectations, is the universe extending an invitation to understand it better. To find the mechanism we missed, or correct the assumption we got wrong, or discover the phenomenon we did not know existed. The scientists studying this are not stunned in the sense of being defeated. They are stunned in the way you are stunned when something genuinely extraordinary lands in front of you, and you realize you are standing at the beginning of something important. So where does this leave us? Here's what we know with confidence. Hubble detected a massive compact object moving through space at a velocity that is inconsistent with standard models of galactic dynamics. The object's mass, in the range of millions of solar masses, makes its velocity deeply anomalous by the standards of everything we have catalogued before. Its trajectory, traced backward, implies an origin in conditions or an event that does not have an obvious modern analog, and the three most credible explanations currently in circulation, ejection from a supermassive black hole, interaction with dark matter, or origin as a relic of the early universe, each carry significant problems that prevent any one of them from being declared the answer. Here is what we do not know. We do not know exactly what this object is. We do not know definitively how it got moving at this speed. We do not know whether it is a singular anomaly or a representative example of a broader phenomenon. And we do not know what revisions to our models, if any, will ultimately be required to account for it. That is not a comfortable place to sit. Human beings, and scientists are human beings, like answers. We like resolution. We like the satisfaction of a question fully answered and filed away. The history of science is partly a history of our struggle to tolerate uncertainty long enough to find the right answer rather than snapping at the first available wrong one. But there is something important in the discomfort this observation produces. Something worth sitting with. Hubble has been looking at the universe for over 3 decades. In that time, it has repeatedly shown us things that changed what we thought we knew. It has repeatedly demonstrated that the universe is stranger, older, larger, more violent, more varied, and more surprising than our best models predicted. And every single time that has happened, the initial reaction has been the same as the one produced by this latest detection. Stunned silence, followed by debate, followed by investigation, followed eventually by understanding that was deeper and richer than anything we had before the anomaly appeared. The object is still out there, still moving. It has been moving for potentially billions of years, and it will continue moving long after every institution currently studying it has been forgotten. Whatever it is, it predates us by an almost incomprehensible margin. It was already crossing the universe when the first life on Earth was still learning to photosynthesize. There's something humbling about that. Something that recalibrates the sense of scale we usually operate with when we think about the universe and our place in it. We found it by accident. Analysts doing routine work looked at routine data and found something that was not routine at all. That is how the universe tends to reveal its deepest secrets. Not in the places we look hardest, but in the data we almost overlooked. The thing racing through space does not care that it stunned us. It was never meant for us to find. It was not sent as a message. It is not a signal. But it is a reminder. The universe is not finished surprising us. Not even close. And the greatest discoveries, the ones that genuinely change our picture of reality, are still waiting at the data we have not yet had the right tools, or the right eyes, or the right moment of accidental attention to notice. This was one of those moments. Pay attention to what comes next.